Thank you very much for showing up to the Physics of Anime. Physics and anime, two things. I'm hoping everyone can hear me fine in the back.
Yep.
Yes? Okay, because I hate miking up. I just can't stand it. I mean, my voice is already loud. I have no such thing as an inside voice.
Thank you.
That's what my mother tells me.
Everyone says it.
Now, physics and anime, I find anime very delightful. It's something I've been watching, you can tell from the gray hair, for quite some time. Definitely an OG, back in the 70s and 80s, anime was hard to come by. But, as time has progressed, we have streaming services, which is, a godsend. Now, on the other hand, physics, something soul-crushing, right? Something that, when we think about it, most people don't want to take it because, I hate math. So again, if you're wondering what kind of demented individual can take something as lovely as anime and something as demented as physics and bring them together, hi, my name's Roman Gomez. I'm really happy to meet you. So we're going to be talking, and I apologize for the small screen. Next time I'll get San Japan to give me a huge one, next time, but if they invite me back. So we're talking about physics and anime. And so let's see here if I can get I had this thing working earlier, but if not, I'll go to this. Okay, so what are we talking about? So we're going to talk about Einstein's special theory of relativity, and in doing so, I'm going to use a couple of old school anime. One of them is called Gunbuster. We'll also talk about the cosmic microwave background. We're going to talk Gotchaman, or AKA Battle of the Planets. It's the first anime I saw back in 1978 here in San Antonio, Texas. Then we'll move the conversation to time travel, quantum mechanics, and Steinscape. And in that case, we'll talk about something called the mini-world interpretation of quantum mechanics. And then we'll finish off with another old school anime. Obviously, if you're talking protoculture, you're talking Macross here. And protoculture, space folding, and you. So, is it far-fetched to think of anime and science? Not so much. If you think about it, there's some really good anime out there that really have science at their forefront. So one example is Cells at Work, back in 2018. And I think if you use Cells at Work to teach kids biology, even though you gotta watch out for the neutrophils going out and cutting everything up, but really, it's all of the scientific principles that are brought forth in that anime are spot on. So again, you've got your erythrocytes, you're carrying oxygen, your neutrophil, your white blood cells. And if you've seen it, anyone seen it? Okay, and you gotta love the platelets, right? Aren't those platelets just adorable? Walking around, doing their duty, you just gotta love them, okay?
Somebody pointed out they should be bigger because...
Another one of my favorites, one of my favorite new animes, Dr. Stone.
Oh, absolutely.
Dr. Stone is so good. Now again, I don't know what the scientific nature of the wave is that petrifies the world, okay? There's a deus ex machina right there. But that's not what we're talking about here. We're talking about the chemical and physical principles that are represented. They're all spot on. They are really spot on. One thing that I learned watching that anime, and again, I have a PhD in astrophysics from Rice University. But again, we physicists don't do chemistry really well, okay? If you get a chemist to do, if you get a physicist to do chemistry, you're probably looking for an explosion sometime soon. So they can generally keep us away from that stuff. But one thing I didn't know is that Edison, his first filament, the first filament that Edison used in a light bulb was a piece of carbon paper, okay? And so in the anime, our hero here, Senku, uses charred bamboo. Charred bamboo is basically just a piece of carbon. You run current through it, and it gives off light. Again, also, if you look at any of the engineering, it's all spot on. So, and I really wish this thing was working. It's irking me right now. So I'll just go to this. Okay, but that's not what we're talking about, jerk, right? Okay, we're not talking about anime that specifically put forward scientific principles. We're talking about anime that let's assume we make some kind of miraculous exception, right? And we know from Einstein's theory of relativity that massive objects can approach the speed of light, but never reach it.
Or exceed it.
Or exceed it. Yeah, we'll get into that. We'll get into that. Can't exceed it. So, but if you make these miracle exemptions, the question is, are the physical principles that are put forward portrayed correctly? That's the question we're asking here, and you'd be surprised that they actually are. So again, if you allow for some of those miraculous conditions, you can accurately explain the effects of traveling at or near the speed of light. You can explain consequences of time travel and quantum mechanics, and you can even, believe it or not, talk about space folding or warping space. So, the first anime, as I pointed out, we're going to talk about is something called Gunbuster. This is the directorial debut of Hideaki Anno, same guy who did Neon Genesis Evangelion, which is one of my favorite anime of all time. Of course, you have these plots. There's an overarching plot, this existential threat. Things are coming to get us, right? And we've got to somehow or another come up with a solution right away to be able to fight them. In this case, we're under attack by a race of insectoid aliens. Our protagonist is Noriko Takaya. She is the pilot of this ultra-powerful robot Gunbuster. This thing is amazing. She, of course, it's a 6-episode OVA series, and in the end, she wins. We conquer the aliens, and Earth, begins to exist, or continues to exist. So again, the science that we're going to talk about here is relativity and cosmology. And one of the things I thought was interesting about Gunbuster was that there are these little science lessons at the end. Just little, 2-minute snippets. And some of the scientific principles they brought forward are kind of kooky, but some of the other ones are spot on. So in science lessons number 1, Noriko mentions 2 principles. 1, space is not an ether field. This is not true. But then she talks about space is 3 degrees Kelvin. Okay, 3 degrees absolute temperature. And we'll talk about this more in just a little bit. But let's see one of the lessons. Let's see if this thing is going to work for me. And manual dexterity, don't fail me now. Can't see the subtitles.
遅れ気味の高谷さんと一緒に皆さんも補習を受けましょうね。今日は第1回でこれから行く宇宙についてです。高谷さんは宇宙について何を知っているの？真空と絶対零度って言うと思ったでしょう。のりこも予習しました。宇宙は真空じゃなくてエーテルフィールドだし、絶対零度じゃなくて国体輻射の3度ですよね。高谷さん、意味が分かって言ってるの？じゃあ初めから勉強しましょうね。そもそもの始まりは20世紀の終わり。カンホイザー博士が発表したエーテル宇宙論で物理学は全て変わってしまったの。カンホイザー博士って5年連続でノーベル賞をもらったすっごい天才でしょ。考古物理学のニュートン、古典物理学のアインシュタイン、現代物理学のカンホイザーって言われています。よくできました。で、彼が予言したのがワープ理論の基礎となったカンホイザーゲートです。スター号でしょ。スター号は単なる亜高速現象よ。カンホイザーゲートは通常物質が高速を超えられる唯一の方法。説明できる？ブラックホールが2つぐるぐる回ってて、真ん中に穴が開いてスター号が見えるだっけ？半分だけ当たり。よくて、互いにシュバルツシルト半径を共有する複数のブラックホールは、その光点角運動の制御によって得意点がむき出しとなり。
Okay, in the interest of not putting everyone to sleep, and also the fact that you can't see me, unfortunately, I always watch subtitled anime. But here's the thing. She mentions these 2 principles. 1, that space is an ether field. Again, this is not true. Space is 3 degrees Kelvin. And of course, she talks about this new big brain, right? We have these big brains in history. We've got Newton. I'm a big Newton fanboy. I'm also a big Einstein fanboy. But then there's this other guy that comes after these people in this timeline by the name of Tannhauser, and he's the latest big brain. He's won the Nobel Prize 5 times. Okay? You know what the going rate for a Nobel Prize is these days? It's like $6 million, okay? And I imagine by this time inflation brought it up, you know? So, you know, this guy's probably rolling in the dough. Makes one want to be a scientist one day if they start throwing money at you like that. It'd be nice. So again, she mentioned these 2 things. Now the whole space is an ether field. That was proved erroneous by something called the Michelson-Morley experiment back in the 1900s. But space is not absolute zero. So this is an artifact of something that we call Big Bang cosmology. You know, we have this theory, right, because we weren't there, but we have this theory that the universe started at this large eruption from a singularity. And so what ended up happening is the high energy state of the universe began to drop as the universe began to expand. And as the universe expanded more, the energy, of course, is going to, on average, drop lower and lower. Now, you'll get to the point where you simply can't drop anymore, and especially in this epoch where we're living right now, there's still a little bit of that energy bouncing around in the form of what used to be gamma ray photons. They are now infrared or actually microwave photons. So what it means is the Big Bang didn't occur, you know, in your grandmother's backyard or somewhere. It occurred at every point in the universe that would ever exist. And so even in deep space, where you think there's nothing, the cosmic microwave background is still there. And so therefore you would never ever, anywhere in the confines of this universe, be able to achieve what is known as absolute zero, a point where all molecular motion ceases. So, Arno Penzias and Wilson, they discovered this. Now the funny thing is, so this is Penzias and Wilson right here, and that's their antenna up there for detecting microwave radiation. These guys were doing their research, and they, again, found this signal coming from everywhere. And they're like, well, what the heck is this coming from? Well, they thought, believe it or not, that it was from pigeon droppings, because they had a whole bunch of birds that were like nesting in there and, you know, doing their business. And so they cleaned it out. And sure enough, you know, it wasn't radioactive decay from pigeon droppings, it was the cosmic microwave background. They found this back in 1978. And of course, you know, won the Nobel Prize for that. Now, honestly, then, if Noriko knows this, she's been doing her homework. Well, what else? So, again, in the interest of time, maybe I'll show you a little bit of this. It's kind of funny. There's one thing that I wanted to show you. I love the coach in this anime. I think that if I can...
ストップお願い科学講座さて今回のお勉強は光の速さの世界についてです。やったワープですね。いいえ超高速つまり C プラス工法ワープについてはまた今度光より少し遅い亜高速の世界ではいろいろと不思議なことが起こります。高谷さんイエビはいスターボーと浦島効果ですそう大宇宙にかかる巨大な虹レインボーを私たちはスターボーと呼んでいるわねローレンツ変換によって宇宙船の前方に集中した星がドップラー効果で7色の輪っかを作るんですよね公式と絵も用意しましたすごいわ高谷さんよく調べましたねコーチの言う努力と根性ですよはいそうですよ
That's what I want to show you.
いつもは
I wanted you to see the coach. Okay? Because, you know, I teach astronomy at a local community college and a local university. And I always wish that I could, like, pop into class like that when people are on their phones or, you know, like, whoa, are you studying what you're supposed to be studying? You know, but again, so she's talking about something called the Hiroshima effect. In relativistic speak, we talk about something called time dilation. And then she's also talking about a change in wavelengths, okay? If you're moving towards something that's emitting light and you're moving close to the speed of light, you're going to change the perceived wavelength of that light. That's called the Doppler effect. And so it turns out that there are certain consequences that you encounter when you are traveling near the speed of light. So Let's see, I also want to give you, okay, this is just, you have to understand the loveliness of my childhood when I got to hear this every.
I guess Star Wars was already canceled.
G-Force, 5 incredible young people with superpowers. And watching over them from Center Neptune, 7 Zoc 7. Watching, warning against surprise attack by alien galaxies from beyond space. Entire galaxy, always 5, acting as one, dedicated, inseparable, invincible.
Okay, so you can picture like 8-year-old Roman like bolting out of my bedroom in my underwear, running to the room to go and see this. And again, this is the first anime I saw, and this started the whole love affair right here. This started. Now, again. This is from Science Ninja Team Gatchaman. That's what it is in Japan. Again, 5 orphans with superpowers. It's really cool. One of the voice actors had a real voice for radio. If you're younger and you remember American Top 40, Casey Kasem, he was one of the voice actors. He was for, I think, Mark. Or I'm sorry, Jason. No, it was Mark. It was Mark.
Voice for Shaggy.
Yeah, and voice for Shaggy. That's right. So their main transport is this spacecraft called the Phoenix. And so the Phoenix, when it's going to move to light speed, it turns into this fire kind of shape, right? Is it a plasma? I don't know. Is it photons? It could be. And that's the argument we're going to make, okay? So we're going to make the argument that a massive material Phoenix can't travel at the speed of light because it's massive. But if you can somehow take all of that stuff and convert it into light, then yes, it's perfectly viable for something to travel at the speed of light. So that's my story, and I'm sticking to it. Okay, so a few things about light speed. So Einstein's special theory of relativity has some interesting implications. So one of them, the laws of physics are invariant. That means that no matter where you go in the universe, the laws of physics that you encounter are the same. The same. It could be in the Andromeda galaxy, M31, which is 2.5 million light years away. Or at the very edge of the universe, okay? Or, I'm sorry, I should say at the very edge of the observable universe, because that's like 46 billion light years, okay? The universe doesn't cease to exist past that point, we just can't see that. It's traveling faster than the speed of light away from us. Now, the other thing is the speed of light in a vacuum is the same for all observers, okay? So everyone will see the speed of light the same, and it is regardless of the motion state of the observer. Oh, another effect, and it's funny, I'll ask my students, what is Einstein's theory of relativity? And they say, well, E equals mc squared. And that's incorrect. It's an effect, it is a consequence of Einstein's theory of relativity, but it is not Einstein's theory of relativity. So this whole E equals mc squared thing is also kind of misleading, because that refers to something known as the rest mass. Every particle that exists in the universe, whether it's moving or not, has something called a rest mass. Okay, protons, neutrons, okay, photons have 0 rest mass, so they move at the speed of light. But if you've taken an advanced course in particle physics, or stayed up too late binging anime, or maybe went out on some other misadventure, you may have run into something like E squared equals P squared C squared plus M squared C to the 4th. Now this part right here is just your rest mass. But this part right here is your kinetic energy, right? It's the energy of motion. And this is the game we play when we're at these large particle accelerators. accelerators. You take those particles, those massive particles, and you accelerate them to the point where they are like moving like 99.9999999% the speed of light. You can never get to 1 times the speed of light because they're massive. But if you take these particles and you allow them to collide and allow them to smish, and that is the scientific term, smish, then there's a possibility in those interactions that you just might be able to make particles that are more massive, right? Because energy and mass are equivalent, okay? That's a very, very important concept. Now, another thing, now we're talking about this whole second postulate, speed of light in a vacuum is the fastest possible speed that you can have. Now, how does this work? Well, here in Texas, we have a penchant for driving vehicles and shooting out of moving vehicles.
Yeah.
Okay. So what ends up happening, okay, there may be alcohol involved, you never know. So if you're driving a car at 100 kilometers per hour, and yes, I'm sorry, I'm using the metric system, I'm a physicist, okay? And then you fire a bullet, right? Fire a gun with a bullet traveling at 1,000 kilometers per hour. Then someone standing on the side saying, "Go for it, Jimmy Bob!" sees that bullet traveling at 1,100 kilometers per hour, okay? 1,100 kilometers per hour. Though this person in the car sees it moving at 1,000 kilometers per hour relative to the car. Now, in the second situation here, I've got a spacecraft. It's traveling at 1/10 of the speed of light. If we could ever make a spacecraft like that, that would be awesome. And they shine a light beam. Well, this light beam is moving at the speed of light, c, relative to that person. Now, this person here should be see 1.1 c, right? No, okay? It doesn't work that way. It does not work that way. You don't get the whole 1.1 c. They do not add. Now you're like, wait a minute, it's the way it works classically, but this is relativistic physics. You know, throw all that other stuff out. Okay, throw all that other stuff out. Because once you start traveling close to the speed of light, your physics changes. All right. So how is this constancy of light possible? You have two effects. So as you approach the speed of light, your clocks start to slow down, okay? What's going on, and this is the only way I can describe it, again, without the I should say, assistance of hallucinogens or anything like that. We have this graph here, okay? So we, as humans, experience time linearly, right? And we never really move fast enough to change how we move through time. So we essentially are residing on this timeline here. If you wanted to know what it's like traveling at the speed of light, I got news for you. You are right now. It's just that you're not moving through space as quickly. Okay? What's happening is you're moving through time almost totally. You might as well be standing still in time. But let's assume that we took some kind of field trip to Alpha Centauri. Alpha Centauri is about 4.2 light years away. If we all took a trip in a spacecraft that traveled at the speed of light, it would still take us 4.2 years to get there. But to our perception, it would be essentially instantaneous. We wouldn't age. We would not age. Basically, your clock would tick, but it wouldn't talk until you arrived at your destination. And again, how does that work? Well, again, when you engage some kind of velocity that is different from essentially zero, then you move off this timeline and start moving closer and closer to this line here, which indicates something moving at the speed of light. When you're moving at the speed of light, you're not moving through time anymore. You're moving everything pretty much through space. Now, if your question is, hey Roman, if I'm speeding in a car, am I slowing down my aging rate? Well, the answer is yes. Yes, but I don't think SAPD will allow you that. Okay? I know. And besides, we're not traveling significantly fast enough, okay? You really got to be moving. Again, the other thing that occurs is, in addition to length contraction, time dilation, where time gets longer, you have something called length contraction. Now, I teach this class called The Physics of Superheroes at St. Mary's. Some crazy person thought it would be a good idea. And one of the problems is I have a meter, I have the Flash running with a meter stick. And if he's running at, 3/4 of the speed of light, how short does that stick get? And you're like, what? Another problem that we had in modern physics was, I have a 50-meter jet and a 30-meter barn. How fast does the 50-meter jet have to fly in order to fit within the 30-meter barn? And then you ask your professor, what are you smoking? But it turns out that this is a relativistic effect, that you actually have objects will, again, have this perceived decrease in length. So again, you have a increased time dilation, decreased length. Again, maybe you've heard of something called the twin paradox, right? You have two twins. One of them flies off into space at half the speed of light, the other one stays here on the Earth. 20 years later, the twin returns, and guess what? The twin who went speeding lives longer, okay? He's aged slowly. And if you don't believe this is a real effect, the United States Air Force spent a lot of money actually testing this. They really, really did. So, and again, you can even experience, and of course it's not in the scale of this, but you can even experience this if you parked outside a black hole, say for a year, because time moves by slower when you're in locations where there's, a greater gravitational field. So if you wanted to get away from the IRS, then you can go and park outside of a black hole. But with your luck and my luck, they'd probably still be around.
The IRS will get their taxes.
That's right. And again, this whole energy mass equivalence, where does this come in? Why can't objects that are massive move at the speed of light? It turns out that if you have mass, it takes an infinite amount of energy to accelerate you to the speed of light. Again, now, if you have zero mass, then as a matter of fact, if you have zero rest mass, then it is a natural tendency for all massless objects in the universe to move at the speed of light. So these photons here, they have no choice but to move at the speed of light. All right, so again, it might be a problem for G-force, but it might be a workaround. This is the kind of math that we have to deal with, which is really fun stuff. I mean, if you're demented like that. All right, so I'll wrap up. Gunbuster. Are the physics correct? The faster an object is moving, the slower it experiences time. There's an example in Gunbuster where Noriko actually encounters her father, who has been dead for 7 years. But 2 days have passed for her father. Okay, she actually sees him. And the Lucian, if you do the math, is traveling at 99.996 the speed of light. Only a crazy person would actually try to calculate that, but I did. Okay, also, I think it's at the end, not spoilers, there's a 12-second delay, and it results in a 6 months of passage on the Earth. This will happen, okay? You travel fast, you don't age, but your friends age, okay?
Absolutely.
It's a sad situation. What about the Battle of the Planets? Well, the physics is correct. Well, again, this is going to take some teasing out. The spaceship, the Phoenix, is a massive object. But again, massive objects cannot achieve light speed, but G-force does. How? The workaround. Okay, the workaround. Become all energy, become all photons, and then somehow have those photons travel as a group. Good luck with that. But I guess it works. Okay, again, photons are light particles. They always travel at the speed of light. All right, so now the time trip. Hopefully, I'm doing well on time here. Before I just start.
Only 30 minutes.
How much?
Only 30.
Okay, good. All right. So, what about Steins Gate? Okay, this is a great anime, and it completely blew my mind. I was expecting one thing, and of course, it shifts. And if you haven't watched it, highly recommend you watch it. Rentaro Okabe, funny character, smart but not a scientist. Of course, She's definitely the brains of the outfit. And of course, it's funny, you inadvertently attract the attention of CERN based on CERN.
Yes.
I've never really thought of CERN as an evil empire, but hey, I mean, it's big enough to go into France and Switzerland, right? So it's the Centre, oh my God. You would ask me that, right? It's basically, it's like the Center for Energetic Particle Physics, kind of something like that. I'm not up on my French. Yeah, my French. All right. So what about time travel? All right. Well, I hate to break it to you. I'm so sorry. Okay. But the scientific community at large believe that time travel backwards is highly unlikely. So you doing this Back to the Future thing where you might become your own dad, kind of there, or mom, or I don't know, is highly improbable. Okay, it violates causality. Now, there is something out there called quantum entanglement, which is really interesting, and we really don't understand it. We think that the biological process of photosynthesis is actually dependent on that. That's why it's such a energy efficient transfer mode. But better yet, how about forward time travel? Can you travel forward? Well, we just discussed that, right? Travel near light speed, okay? Travel near light speed, everyone ages and you get to travel forward in time. Or again, like better yet, camp outside the event horizon of a black hole. Do not go past the event horizon, okay? It's funny, one of my students asked me one time what it was like to go into a black hole, and I told him, Paul, I don't know. But I have been married and divorced 3 times, and I imagine the sensation So now, there are some snippets of the community that think that traversable wormholes. So you can have 2 different types of wormholes. You can have a wormhole in space, or you can have a wormhole in time. A wormhole in time allows you to be 2 places simultaneously. A wormhole in space allows you to be at 2 times simultaneously. That's some heavy drinking involved there.
Sometimes science involves a lot of heavy drinking.
Dude, just talk to George Gamal. Absolutely. So again, the jury is still out on that one. The jury is still out. Right? We can't say. I always say this: if you take a pie chart of the universe and you put down exactly what we know about it, it is a sliver that's about 4%. I mean, there's like 96% of the universe we know absolutely nothing about. So would you say there are employment opportunities in this field? More than likely. So
the more we find out, we don't know.
That's right. That's exactly right. Right. The more But I know enough to know that I know nothing at all. There you go. All right, so of course, during the course of the story, some particularly bad things happen. There is one character you just can't seem to kind of keep alive, and it's really kind of sad because she's just a wonderful character. You got to love her to death, or at least. So let's see. So again, the worst of those things. What ends up happening?
If you're having trouble getting your head around the concept, it might help to think of world lines like fibers in a rope. At first blush, a rope looks like a single thing, but hone in and it's obviously made up of many interlocking threads. Now each thread is its own thing, independent of its neighbors, but they're all moving in the same direction. That's why it's so strong.
Wait, are you telling us that every world line leads to Mayuri's death?
For now.
Okay. Just stop it right there. Because I don't want to talk about it anymore. All right, so this whole thing are multiple world lines of viable scientific theory. And it might surprise you to understand that they are. Okay? So quantum mechanics is one of our pillar theories. I just talked about the first one, right? Special and general relativity, quantum mechanics, and these things are like 2 kids on a playground. They do not play well together, okay? They don't. General relativity talks about things really, really big. Quantum mechanics talks about things that are really, really small. And again, neither of the twain shall meet. But it explains things, the behavior of things like electrons, photons, atoms. It's a pain, okay? Einstein was one of the fathers of quantum theory. And to his very end of days, he attempted to disprove it. okay? He couldn't stand it. He didn't like the statistical nature. It never gives you a straight answer. It's like a teenager. If there's any teenagers, I don't mean to trigger, but I used to be a teenager too, and I never gave my parents a straight answer. Okay? So again, what's going on here, it gives you a statistically viable, it's like, well, it might be that way. So again, a perfect example of this is the Schrodinger's cat experiment, okay? And if you ever try this, you are a horrible human being, okay? Leave those poor cats alone, they did nothing to you. But what's going on here is you've got a cat that is half living and half croaked. Now, how does that work? Well, again, the experiment works by putting something in there that can kill the cat. You close the box, and then you ask yourself, okay, is the cat living or dead? Well, when you open the box, you find out which state has prevailed, because it's called collapsing the wave function, okay? You've taken this entire wave of probability and then collapsed it to one finite conclusion. But until you open that box, everything is just kind of wavering around. So how do you rationalize this? How do you make this make sense? Don't you just love it? This is what we call Brocket notation, okay? Dirac came up with this one. So again, this is the quantum state. Half a cat living, half a cat croaked. This describes its wave function. But again, once you've opened it, then to determine, and this is where the multiple world lines comes in. When you open that box, there are two probabilities, right? And so if you're going to figure out which universe you are in, you open the box. If you open the box and the cat is living, then you're rest assured that there's another universe where the cat died, okay? That's how this stuff works. And again, that's the whole thing with majority, right? This is the majority wave function. So what you had to do is move, it's not that majority moved, it's that you moved to another state, another world line where majority is still alive. Rest assured, there's still that other world line where she passed on, but you're in a different world. And of course, this is it's by a guy by the name of Alan Aspect. It's called the multi-world, many worlds interpretation of quantum mechanics. It is a viable quantum theory. All right. Now, thankfully we'll get done here and I can open the floor to questions, because hopefully you guys have questions, or you're either just bored and like, let's get that, got it.
I have questions.
Well, I'll give you one, just a little bit, I promise. All right. So, space folding, warping, and protoculture, okay? Superdimensional fortress Macross. I binged the heck out of this when I was in the Army, because there wasn't much else to do when you were back from the field and you had no money. So you'd walk a mile to like the nearest video store. They'd let you like rent 3 tapes at best, so you're like walking back, go to the barracks, watch them, then walk back. That was binging back in the old days, right? It's not Netflix judging you saying, are you still up or are you still watching, you know? So again, this is one of the classics. The Americanized version is Robotech. Again, this whole existential threat, alien species from a distant galaxy past the Milky Way are attacking it. This Macross ship, or this ship lands on Macross Island, of course, SDF-1. They reverse engineer. Now that's pretty amazing, okay? They reverse engineer this, and now they have this ship that does something, but they don't exactly know what it does, okay? It's like giving a kid just a bad toy, right? Giving an infant Tinker toys and say, okay, go play. That's kind of like what's going on here, but we're going to go with that. What ends up happening is they have this sudden attack by the Zentradi, and they push a button. It's like, what does this button do? And the next thing you know, they're warped to the very edge of the solar system, okay? It was a completely uncontrolled jump. And they're lucky to have gotten to the edge of the solar system, and they have to fight their way back. So there we go. So here's the setup. You've got Hikaru Ichigo, or Rick Hunter in the Americanized version. You've got Lin Minmei. They're escaping from these Zentradi warriors. Hikaru's plane is just outside of the fortress. And of course, the situation's crazy. You need desperate action, and you need to get out of there, and you need to get out of there quick. So again, with really no other choice, the commander, I believe his name is Global, Henry Global, activates this jumping mechanism and all kinds of craziness ensues. And I'm trying to see, yeah, this is it. Last video, I promise. Just feel it, okay, because there's no subtitles.
本土突入10秒前9、8、7、6、5、4、3、2、1、0。
本土突入
Yeah, let's not just the planet, not just the ship. Let's take half the planet and everything around it. Why did you push the button? Whoa! It's a long, drawn-out space bowl.
地表付近でホールドするなどとそんなことはでき
Every time freaking out.
私にも分かりません
直ちにデフォルトポイントを探し出せ了解
And there you go. Yeah, let's just say, I like the way that they included the sky, right? Somehow or another, you're able to pull the sky. And yeah, well, the water is a no-brainer, but right, you bring the sky with part of the atmosphere, but come on, yes.
Everyone on the island, duh, right? Because once that field dissipates, like,
Everyone was in shelters, that were right.
Yeah, everyone was in shelter, so they didn't die. Yeah, that's crazy. And they recovered it, okay? So hold on, so we'll get to this. So how do you warp space? How do you warp space? Hold on, give you a chance. So we have this Einstein-Rosen bridge, okay? And this is a viable mathematical conclusion to Einstein's theory of general relativity. It is that a black hole can connect 2 points in space. That you're essentially can be there simultaneously, okay? Space-time is folded, so that the points momentarily occupy the same location, and then you unfold space. And that gets you to where you went from where you were to where you are now, kind of deal. Right, again, when the transit is made, the wormhole is relaxed, space-time returns to its normal state. Again, this is consistent with the theory of general relativity, and it does allow faster than light travel. So, Han Solo fighting at light speed or something like that is probably not going to work, above light speed isn't going to work in this case. Another thing, there's something called the Alcubierre warp drive. So when I was an undergraduate student, back in the 90s, yes, I'm old, there was this guy by the name of Miguel Alcubierre. He's a Spanish astrophysicist, and he made, when we worked in special relativity and general relativity, we use things called metrics. And so this is a matrix or a tensor. The reason why we call them tensor is because the more you work with them, the tensor you get, right? But this is a real tensor. It's a real mathematical quantity, and what it allows you to do is to elongate space behind you and truncate space in front of you. Now, here's the trick. If you can get a spacecraft that moves an appreciable portion of the speed of light, and you're moving through a truncated space-time in front of you and an elongated spacecraft or space-time behind you, then you are globally, with respect to the universe, traveling faster than the speed of light, even though within your little bubble, you are not breaking the speed limit. Now, what this takes is a huge amount of what is known as negative mass. Negative mass would be repulsive. You're like, what? And this is the crazy thing, because gravitational fields, as far as we know, gravity is an attractive force. As I'm standing here, you are all attracted to me in a gravitational sense. In a gravitational sense, okay? Really not that easy on the eyes, trust me. So I'm talking gravity here for sure. So, again, you are locally traveling, again, towards the speed of light, but again, because of that truncated space, you are traveling faster than the speed of light. And again, you can check the math out. Cuvier's paper in 1994. That was one of the things that got me started in this field of study. It's just amazing stuff. So, in conclusion, do we watch anime because we're trying to make sense of science? Well, God, I hope not. Okay? But it is useful, okay? And it does stimulate the imagination. Case in point, when I was writing my master's thesis, I had so much dark matter quantum mechanics going on in my brain, and I needed something to just, please save me. Thank you, Bleach. Bleach. I finished the entire Soul Society arc, and it kept me sane. Thank you, Bleach. But here's the important thing, you know, we need imagination. You know, the thing about Einstein, it wasn't his mathematical prowess that was so amazing. It was his imaginative use of math that already existed. It was the fact that he asked the right questions. And the question is it even possible? And if it is, how can I make it a reality? So, I mean, again, all great discoveries are going to start with questions and imagination. So I hope you enjoyed my presentation. I hope you enjoyed the rest of the convention. And thank you so much. Thank you very, very much. So now I can open the floor to questions, comments, and complaints. All right, so you are...
This is, I guess this leans more to a philosophical question than a sense question, but maybe a little bit. So, many worlds, like world line theories. So, for one, I find it kind of, at least sociologically depressing that, like, you know, a character that goes back in time onto a different world line to try and change history isn't actually changing it. He's literally leaving a dead universe behind, and he's becoming English. Yep. So, aside from the fact that that's really fucking sad, at least narratively speaking, in the beginning story, does this not, I guess, further lend evidence to, I guess, not just the individual, but I guess a cosmic lack of free will? Because if...
Dude, you are like getting into some heavy stuff, right? I just don't know. I mean...
Like, if you're in a universe where, like, where Hitler got reelected for the 80th time, and then you found out you the world launches were made, like, an advanced machine, you figured out the only reason you're in this universe is because people already made a decision, or at least somebody's made a decision. I think universe where everything is great in that universe, but then you're like,
I think this is a question that we can discuss over beer. I mean, that's certainly more appropriate. Yes, sir.
Yes. So when you say when you're going faster, you age slower, correct? Just do a recap. So in theory, I can't say it's feasible. If I was a character from the anime Initial D, if I keep driving all over Japan, provided that I'm constantly fueled while on the field, would that mean I would age way slower and have an existential crisis?
You probably would. You know, it's funny. In NASCAR cars, while they're driving, their drivers are going to age slower, one, and also they have an appreciable increase in inertial mass because of the velocities at which they're traveling. That's something a lot of people don't know. Oh, yeah.
Really?
Yeah. Yes.
So you mentioned that with the light cone, the clock ticks, but then it doesn't talk until you get there.
That's right.
Would there be any effective difference in your perception of reality of traveling at light speed than to taking a wormhole or something like that?
No, it'd be basically the same, right? Because you're instantaneously traveling. In your perception, you're instantaneously traveling. So it's essentially equivalent to fold space and occupy two places and to actually travel at the speed of light. I'm going to get that gentleman, and then I'll get your question, sir.
Sort of two questions, and if I can only ask one, I understand. So if technically we could find a way to make us weightless, is there any way to make us weightless yet? Would we then tend to go to light? And
that's exactly right. So this whole teleporting thing is like, well, I can go faster than the speed of light, I can teleport. No, right? Because what ends up happening when you teleport is you convert your information to light, then you travel at the speed of light, and so let's assume that you were teleporting, right, to Alpha Centauri. Somehow or another, you'd have to use the materials at that location to reform you. And then the question is, am I even me still? You know, am I even me? You know, what are we? What are we?
Then you're sort of doing alchemy almost.
Exactly, exactly. Yes, sir.
Two beams of light pointed at each other. Would it be accurate to say that the mutual closing speed is 2 times the speed of light?
No, there's still the speed of light. Yeah, I know. It drives one up the wall. Because what ends up happening, we use that principle for combining ions, combining atoms. And here's the thing, if you were going twice the speed of light, well then you should have, you know, multiple amounts of energy. No, you always have a certain amount of energy, and it corresponds to the speed of light.
Huh.
Yeah, it's crazy. Let's see, if there's a gentleman with, or yes, you in the back.
As density is, the density on an object is, more gravity it generates.
Mm-hmm. Or the more mass it has.
More mass it has, more gravity it has.
Yeah.
Is there a limit to how dense you can make an object?
There isn't a limit to how dense you can make an object, but what will end up happening is you get to the point where the escape velocity of that object exceeds the speed of light. And when you get to that point, that is something that we more affectionately call a black hole.
Yep.
Can you make a marble, something so dense as of a marble that has the gravity of a black hole?
Yeah, I mean, yeah, you could, I mean, well, okay, it's kind of tough. So, can we make it? I mean, there are cutoffs, right? If something has a mass of greater than 3 times the mass of the sun, then that will form a black hole, and the black hole will have a radius of about 3 miles. That's right. Whereas, like a neutron star is like, has the, if you took you and collapsed all the space between your particles and you were turned completely into neutrons, so there was no chance of electrostatic repulsion, you could achieve the density of a neutron star, but the cutoff, I think it goes from 1.4 solar masses, that's the upper end of mass for a white dwarf star. And so from that point to 3 solar masses, you end up with a neutron star, and a neutron star can have a radius that's about 6 miles. 6 miles. Let's see, San Japan in the back.
Yeah, the transport concepts with space folding, are they orb-based like Macross, or is it kind of shapeless, or does it not matter?
Again, the one that's depicted in Macross, I'd say is more like, would be, you know, it would be a wormhole. You're kind of locally making a wormhole that opens up elsewhere, in this case, in the outer portion of our solar system.
Okay. The transport, though, is that kind of shapeless, or is it?
It's shapeless. You're kind of like you said, they kind of took an entire, well, I don't know how accurate that is, right? But it's anime, right? Let's see, this gentleman wanted to ask a question. Did you have a question?
Yeah. Is there anything to say about how any difference between outer space and in-space heat transmissions regarding speed of light?
Again, you mean like being able to travel? So, okay.
Being able to transmit messages through space.
The only one that we've seen that you can theoretically transmit information faster than the speed of light has to do with this quantum entanglement problem, right? This whole, if you make something spin up over here, this one has to be spin down, and there's a necessity. And so the question is, how do you transmit that information when these things have a certain distance? That is right now one of the biggest puzzles. Look, again, we don't understand everything about physics right now. And honestly, the thing that keeps me doing my job is the stuff we don't know. It's the sheer immensity and the sheer wonder of the stuff that we don't know. That's where the money's at. That's where, by money, I mean that's where the
grant.
No, not the grants. I mean, believe me, you know, it's just that's where the passion lies. And that's where it has to lie. Because if it doesn't, then why are you doing it in the first place? All right, this gentleman had a question here, then I'll get you, and then I'll come back to you. Yes,
I feel our wormhole is only possible, right? Because you need something on both.
Exactly.
At the start, at the end, so probably something like quantum entanglement, right?
Yes.
If you pre-place it, you can create like a fixed black hole, but like what we see in science, like just warp anywhere, like that doesn't seem.
Yeah, it doesn't seem.
Right.
Yeah, there's got to be some kind of method behind the matter. Right. Yes.
Has there been any real-world observations or applications of quantum immortality concept?
No, not to my knowledge. You know, I had a friend of mine when we were going to undergrad together. He was like always talking about the philosophy of quantum mechanics, and I was like, I need to think more about this stuff. You know, because I mean, I am a doctor of philosophy, which means that I'm legally entitled or legally bound to give you my opinion, but I don't want to give any bad opinions. You know? Yes, sir.
Okay, so 3 different questions about negative mass, Hawking radiation, and gravitational waves. First one, about, like, from what I recall, don't most black holes emit Hawking radiation?
They're supposed to, yes.
And
that's,
so
I think that's been proven.
And how does this reconcile with the supposed absolution of the event horizon? Is it just that, like, since entropy must always increase, at least on a cosmic level?
Entropy always increases, and that's a funny thing, right? Because black holes are funny, right? Because if you look from a classical point of view, black holes are infinitely well-defined, right?
Yeah.
But if you look at it from a quantum mechanical point of view, well, quantum mechanics doesn't like that, right? Again, a very good example of this is the Heisenberg uncertainty principle, right? That you can't simultaneously know how fast an object is moving and its position. If you exactly know what its position is, then you have no frickin' idea how fast it's moving.
Yeah.
And so I think that if one were to, and again, this is just my opinion, it was something I suggested in grad school, but now since I do space, solar physics and stuff like that, I've moved away, which makes me sad. But if one were to maybe engage some kind of Heisenberg type analysis of that boundary, I think one could come out with some interesting stuff.
Okay.
You know, maybe some kind of conformal analysis. Yes, sir.
So, hopefully you can hear your question. In Star Wars, when they are moving at the speed of light,
Yeah.
there's no way they can. So they're like, oh, this one's moving faster than the in speed.
Yes, no, there's no way. There's no way that you can see that. No.
They can catch up.
Ludicrous
speed.
Yeah, ludicrous. Ludicrous. It's going flat, right? That's it's going flat.
Light speed's too slow.
It would be like, well, look, we're moving at 10, but they're going to 11, right? And it's always better to go to 11. You know, again, no, you couldn't. And that's the funny thing. Like, what's one of my? So I watched the reimagined Star Blazers. Has anyone seen that one? It's really a beautiful anime, but they have those. They have this sub, but the subs go into like a hyperspace, and then they have a periscope that like looks into regular space, and they're able to fire torpedoes. And you're like, this is kind of cool. I don't know if it's entirely possible, but this is really, really cool. So
We're messing with your mind and we're messing with quantum space to shoot a torpedo at you. That's something that definitely sounds like something the American military would do.
Yeah.
We're gonna.
How are we doing on time?
I think we're over time.
Yeah. Okay. Okay. One more question, and then so let's see here. I've got 2 people here.
Mine is unrelated to your topic, but he can go first.
Okay, go for it.
Okay, so the last 2 questions were negative mass and gravitational waves.
That's right. Okay,
so
sorry.
gravitational waves. So like a couple years ago, 2 black holes collided. We noticed the gravitational waves here on Earth by using like lasers, and then expanding and contracting. That being said, since our perception doesn't change even when like we get near the speed of black hole vacuum, how is it? Then that confuses me because which is really cool. But like, how is it that we noticed the lasers yeah? How do we notice lasers changing if like the gravitational wave itself? If it's really big in space, but we're still in space, and so how are we
if I asked the same question.
How can we notice the fishbowl moving since we're still inside the fishbowl?
Well, remember, so that fishbowl is perturbable, right? And again, what you're actually detecting, and it's really kind of spooky, the space in which we exist is quite literally, and it can be, well, how can I say it, dimensionally independent, right? Remember, the disturbances that this thing detects are 10 to the minus 21 meters. 10 to the minus, so it's funny, when I was looking at going to graduate school, there were 2 places I could have gone. Rice University to do dark matter research, and LSU to do gravitational waves. I got accepted to Rice, and I was like, okay, great. LSU said, hey, we just need your letter of rec, or statement of purpose, because you have a good packet, let's go ahead and get you in here. I was dating Evil X number 2 at the time, and I think that moved me more towards Rice. Okay, since then, not only have the LIGO detected gravitational waves due to black hole mergers, but also to neutron star mergers. Ooh. But they did that on multiple situations. No one's found dark matter. I sometimes think I backed the wrong horse. But again, those disturbances are incredibly small. Smaller than even an atomic disk.
Like near the Planck scale.
or something. Yeah. Well, plane scale is much smaller, 10 to the minus 57.
Oh, yeah.
Yeah. So.
I thought we discovered dark matter around certain galaxies, but we just don't know what.
No, that's what it is, and that's really what it is. So we have indirect evidence for dark matter, right? We've got gravitational velocities, rotational velocities, rotation of clusters, rotational velocities of clusters, all of these things. So it's funny, we see something there, right? It's driving us nuts because we see something there, but it's so hard to detect. I mean, it might as well be the ultimate introvert. I mean, it's just. So I think my time is over. I really appreciate the questions. I really appreciate you guys coming in. Thank you so much. Thank you.